All right, guys, this is not the first time you guys are simulating a transistor. You have done that in logic. But what you did over there was just pure digital. So you put the PMOS on top, NMOS at the bottom. You probably didn't understand what are these devices in that class. And then you put them in the symbol and make a gate out of it, remember? So you simulated all the digital logics. So now we are running all the possible input signals into it. So you can see we are doing a DC sweep. I don't know why that one is not opening. But you can see this, right? You. One remote. If you want to grab an NMOS over here, press F2. Okay. And F2 will open up this library, and you slide this to the right hand side. You can see there are a few options for the transistors. So the ones we are going to use is NMOS 4 or PMOS 4. So 4 stands for the 4 terminals. So P-type MOSFET or N-type MOSFET, but has 4 terminals, which means the drain, gate, source, and body. So body is a P substrate. We'll talk about the body later this week. So body is a substrate, which is the substrate makes sense. Is the body of the wafer, the transistor, and the body is always shorted to the ground. That's how we operate it. We'll explain why later. Okay, just for the NMOS, you always short it to the lowest potential in the circuit. Okay, so got a ground here. I can see this is not. It was not there permanently. I connected to it to the body contact. Okay, and source is a source of electrons, and drain, the drain of electrons, the gate. Okay, and what I want to plot, remember yesterday I talked about the IV curves. So if you have a VGS, what is G, what is S? Quick question, what is G, what is S? What is G? Gate, S. Source, D. Drain, S, source. Okay, so IDS is the current from drain to source. Okay, from drain to source. Current from drain to source means electrons are flowing backwards, right? That's why it's the source of electrons. Here's a gate. So IDS is the current flowing from top to bottom, and VGS is the voltage potential in between G and S. That's VGS. So now we are engineers, electrical engineers, we are learning how to operate this transistor, keep in mind. We just bought this transistor and we put it in the lab, we'll learn how to use it. That's what we are doing now, right? So first, how do we want to, the way to open this up, because transistor, you can turn it on, turn it off, just 2 states for digital. In analog, they have millions of states, different voltages, but in digital, it's just on and off. Okay. Now the input voltage could be 0, 5 volts. Depends on the digital voltage, right? Digital is just 1, 0, right? 1, 0. 1 is logic 1, which is 5 volts in this case. Okay. So 5 volts being provided here. So what is the VGS usually if you ground here? If you put a 5 volts to the gate, what is the VGS? 5, because the source is grounded. So 5 volts, if VG is 5 volts, VGS is going to be 5 volts as well, because VS is 0 volts. So VGS equals VG minus VS. That's why we call it VGS. Is the voltage potential difference between G and S. So VGS must be larger than the threshold voltage called VTH in order to turn it on, turn the channel on, okay? Doesn't have to be fully on, because VGH is only 0.8 volts for this technology, only 0.8 volts. So if you give a 5 volts, it's pretty much fully on. But if you only give like 1 volt, it is still on, but only has a small current flowing from top to bottom. So for VGS versus IDS, the IV curve looks like this. And here is the threshold voltage. That's how that works. We didn't design or fabricate the MOS transistor by ourselves. We bought it. And that's how that works. Don't think it's too much. It's just we bought a device, we plug into the board, we provide a VGS, IDS is going to flow that way. That's it. That's how we use it, all right? So this is for VGS versus IDS. And now let's do a simulation. I'm going to put this one. I'm just making a copy VGS, IDS. Okay, because I'm doing a DC sweep for VGS, so I'm going to keep this one. This is .DC sweep for the x-axis, and VGS is a parameter from 0 to 5 volts and 0.1 volt for each step. And since I'm not doing this command this time, so I'll just delete it. And this is the model file for the transistor. I have to include it in here. I'm going to show you the model file in a bit. And this one, because we are sweeping VGS, so I have to keep VDS on at 5 volts. And this looks odd because VGS is only 0 volt. You can give any voltage to VGS for this case because we are doing a DC sweep. We are changing this anyway. So this one is going to override this parameter here. I mean, it's okay you give it 10 volts. It's not going to change the result because it's not being used at all for this simulation. Why? Because I'm doing a DC sweep for VGS for this guy. So this is going to override it. Okay, so this is not doing anything. I just put 0 volts here. Okay. So VGS will be, the x-axis will change over time continuously, and we're looking at IDS in this case. We're not changing VDS because VDS is just a constant for this case. We have to keep it on when we sweep VGS. You cannot sweep both VGS and VDS at the same time. But you can make a list. I'm going to show you that later. But now we keep VDS as a constant, and we're do a DC sweep for VGS. And the transistor, how do I change the width and length? We haven't talked about that yet. But the way to change it is you have to press Control at the same time, right click, and bring this window up, and you can see the parameters here. Double click, you can modify it. And in your case, probably this is not checked. You double click, uncheck it or check it in order to make it visible or invisible. So since I checked it, so that's why it's showing up here. I can see the width and length of the transistor. This is the model file's name, the name in the model file of this transistor. And this is the name of the transistor in the schematic. So when you are modifying the model name, do not change the M1 or M2, so on and so forth. These are names in the schematic, not a model name. So for example, if I just grab another one, see? If I want to change the model name, where's the model name? It's in the model file. This defines all the physics, the physical parameters of the transistor in the process. So that's defined by the manufacturer or the foundry. Okay. So for example, the Tox, which is the thickness of the oxide, which is this much, right? VTO is the threshold voltage, which is 0.8 volts. Kp is another parameter, which is a combination of all the dielectric constants together, and we're going to show that parameter later, maybe next week or 2 weeks from now. And the capacitors, some of the capacitance in the transistor or in the different layers. Just a whole bunch of different parameters in the process. And this is a short version of it, simplified by, I believe, Dr. Baker from the textbook, who wrote the textbook. For example, the TSMC 180 nanometer technology, I think the parameters are probably like over 10 pages. These are just one little paragraph. It's simplified, oversimplified, just for the textbook for educational purposes. But at least it covers threshold voltage and covers the basic capacitance of the different layers, right? So that's for the NMOS. That's for the NMOS. And the model name is N_1U. Okay, keep in mind. Sometimes, I believe, maybe the one you're going to use for electric is, I think the name of the model file is called C5_models. So I have to open it up and look at the model's name. It could be just NMOS instead of N_1U. So it's called N_1U in the textbook is because all the models being used in the book is based on the 1 micron technology. It's a huge technology. It's like a fake version just for simulations. You're not able to fabricate it because first it's too big. Cannot see any foundries are still fabricating anything for it. Second, these are just a oversimplified version of it. So N_1U is the name of the NMOS transistor in this model file, and P_1U is the PMOS, the P-type MOSFET in the model file. And these are the 50 nanometer technology, but still an educational version of it in the book. You can see it because it's smaller per size, 50 nano versus 1 micron. So you can see there are a lot more parameters to define the features of it. So it looks longer. It's a short channel model version in the book. Okay. So this is where you find the name of the models. That's why we have to rename it here. So this is the one I just grabbed from the library, right? I can see the default model name is NMOS. Okay, but we have to change it to N_1U. How to change it? Just right click on the name, on the text, and type the name here, okay? Change it to N_1U for the NMOS. You're not changing M2. Okay, it's a number or it's a name in the schematic, M1, M2. If you grab another one, it's going to be M3, okay? Change the model name, don't change the schematic name here. So, delete it. Is that clear for all these parameters here? M1, N_1U, the length and width of the transistor. We're not trying different dimensions of it. Just use 10 micron for the width and 1 micron for the length. So it's basically just a W and L, lowercase. Okay, so make sure you have your simulation file and the model file in the same directory. So when you directly put .include models.txt, it is able to find it, the simulation file. Okay. So now I'm going to run the simulation. How to probe the current? You see this red probe, this little thing is probing voltage. It probes voltage. But I have to put in pretty close to the drain of the transistor. You can see there's a black probe, has a circle on it. That's a current probe. Okay, and it's not going to show up here, but only when it's getting closer to a component, it shows that current probe. You can see this current probe has a little arrow pointing down. So whenever you probe it, it's showing the current flowing from top to bottom. So is that going to be the same current if I probe here or probe here? Keep in mind, we are looking at VGS versus IDS. Okay, so there's a current flowing into the channel of the transistor from top to bottom, right? There will be a current flowing from top to bottom in the channel. Okay. If I probe here and probe here, are they going to be the same current? The gate doesn't have any current flowing into it.
But like the same current.
There's just one loop.
Yeah.
There's just one circuit, right? If I probe it here, so it's probing, it's detecting a current flowing from top to bottom. If I probe here, it's IDS from top to bottom. Are they the same current?
Yeah.
Hmm? So the current IDS is pointing down, right? Still the same current or not? What is this one probing? See the red arrow here? Could you see that red arrow here?
Be the same magnitude? Like it's just defining the way.
Yeah. Same magnitude or same amplitude of current, but opposite direction. Because this one is draining current that way, right? Counterclockwise. But this guy's moving down, so it's clockwise. So if I probe it, they're saying, hey, it doesn't make sense. This one looks like this, go up. But this one is just opposite direction, same current. So you can expect somewhere here will be 0.8 volts or negative 0.8 volts. Which one? Negative or positive? Positive. Yeah, so x-axis is not being inversed at all. Right? So still positive. Right? Is that 0.8 volts? Pretty close. As a threshold voltage. Okay, so if I probe the transistor's current, okay, looks exactly like what I drew here. Okay, make sense? And there's a way that we can try different VDS. Now we just keep VDS as a one value here, and there's a way that we can change it. So type this number here and have the curly bracket and name it at X. It can be any name, doesn't have to be X, but I would just name it at X. And come to the code here. And sometimes you want to type multi-lines in the Spice code. So the way to do that is because if you only do a single right click, or you can close it, it's going to bring up the other window. But there's another way to do that, which is control right click. So it's going to bring up this window, which can handle multi-lines for the Spice code. And if you want to add a line in the middle, you don't want to directly press enter because it's going to close the window. By default, OK is enter, right? So what you want to do is control enter. Start a new line instead of closing the window, and put a dot step as a function, dot step. And I believe it's parameter, step function for parameter x. And let's try 0, 1, 2, 3, 4, 5. I think that's how that works. Let's try it first before we find out the truth. I'm going to rerun it. Oh, this doesn't work. There's another, I think it's VDS.
you have a place to download that models file?
Yes, it's on the website. Let me show you.
I thought it was a logic, but I couldn't find the logic.
Here.
Okay, that's in the digital.
Teaching, but for 2022.
Yeah, thank you.
Let me see if that's a model.
And it's both of those files?
Let me see. Okay, so C5 is the one used for the lab.
Okay.
And this one is a model file from the book. Okay, the same one that I just I'm using right now. But you wanna, because I have to every time I have to type cmos.edu.models.
Yeah.
So I just delete, just delete this. Just use models.txt. You found it? Hmm. Did it work for everyone? Did it work for you? Did you find it? Okay.
And where do you put it? You put it in the libraries folder?
No. So start the LT Spice, right? What I did is just start LT Spice and save the file, save as to the desktop. That's what I did, just put in on the desktop and put a model file in the same directory. That's what I see, model file.
Oh, I see.
The simulation file. Right. Mm-hmm. Okay. Yeah, I was not expecting you guys to do the same simulation at the same time while I'm talking. I just want to, I'm recording it, so that's why I didn't give you the model file and everything. I was just let you guys follow. Let's do it real quickly, and then you guys will take the time to do the work. It's okay if you want to follow. So I think I missed probably one little thing here. Oh, I missed the list. So that's a keyword here. So it's basically dot step and to put a list, right? Okay. Dot step param x list 0, 1, 2, 3, 4, 5. Include models. So what's going to happen is going to plot all these different VDS. But how can you tell which one is 5 volts, for example, for VDS? Which one is 4 volts? Which color? So higher VDS will be on the left-hand side or right-hand side, or top or bottom for higher VDS. Higher VDS will be on the left, right? And lower VDS should be here. So this one is 0 volts because 0 volts of VDS is not giving you any current. The channel is off, no matter what, no matter how you change VGS. Okay, how could you tell from the other way? Click Control Panel and go to Color Scheme. And that's Waveforms, Color Scheme. You can see trace 1 is black, and trace 2 is this light blue color, I think. It's not changing here. It's not changing in the little window here, but it shows all the different colors over here. Okay. So I believe this didn't follow that. Did it follow it? I don't think these colors follow these parameters here. It's not using black at all. Always because the window frame is black. That's why it's trying to avoid it, I think. Maybe, yeah, anyway. Okay, but I don't think there's another way to tell which one is which, you know, or adding a label to it. I don't think LD Spice can do that. But you should be able to tell like which one is which, okay? So you know 5 volts should be on the left. Okay, so this is for sweeping VGS. So what if we put a 5 volts for VGS, and we're sweeping VDS, so we just put a 0 there. It doesn't matter, it's going to override it. Okay, and we change the parameter to be VDS. Okay, and I don't want to use this step function for this simulation. I'll just add an asterisk in front of it. So I'm commenting out this line. So this is not being executed. Okay. It's basically just have a certain VGS and a sweeping VDS. So yesterday I did it really quick for you guys. Save it on the desktop. For VDS over versus IDS, again, this is a device we bought, and we are looking at the user menu, right? If you apply a VDS, you're getting an IDS like this. It saturates at this voltage. And that is because pinch off of the transistor. You don't have to know why it happens, right? It just happens. So this is N plus. So after pinch off, which is like this layer is going to keep moving to the left, but the electrons is still able to tunnel through this layer and reach the drain. But after this state, the current is not changing, it's not going to change significantly anymore. It's going to be pretty much just flat, okay? That's a user manual, right? And then we just run it. You can see it's pretty much flat. It's not perfectly flat, but you can see it's getting saturated. And if we want to have different VGS, let's call it X again, and remove that asterisk here to uncomment it. Okay, and now we are sweeping VGS. Rerun it. Oh, DC sweep. Sorry. Yeah, it should be VDS. Sorry, I shouldn't change that. What else should I change? That's it. I don't need to change since I'm doing DC sweep for VDS, so I shouldn't change it to VGS. Anyway, so let's run it. See? So there are several lines getting saturated at different voltage. And which one is higher, which one's 5 volts? Because you can see I have 0, 1, 2, 3, 4, 5 on the list. So these are different voltages for which the parameter here. VGS. And we're sweeping VDS. So the x-axis is VDS, and these are different VGS. If you have, for example, what happened over here is, for example, pick up voltage 3, right? So 3 volts. If I have 3 volts for VGS here for 3 volts, okay, constant, not changing. And then I do a sweep, DC sweep for VDS. going to be the purple line. So this is 4 volts, 5 volts. So bigger VGS will give you a larger current. It's going to saturate the different voltage as well, or current. So these are, you got a 2 or 1. 2 here, right? What are the 2 voltages? The red one, the other purple one. 0 and 1.
Was that 1 volt not high enough over the 0.8 volts to pretty much?
Just 0.2 volts bigger than 0.8. You can see it's just barely on. Current is low. So which means if you have a bigger VGS, you got a bigger current. Like the valve of the channel, right, or the pipe. You turn on the valve more, give more turns, you got a bigger opening in the valve or in the pipe. And then you can allow more current or more water current to flow in the pipe. Same thing, same concept. So if you want to get water flow in the pipe, first you need to turn on the valve to have an opening in the pipe. Okay. But if you don't have a pressure difference, then the water will stay there, not moving at all. It's like the electrons being attracted to the channel, form a channel of electrons. It's not moving at all. So that's why if you keep VGS, just no matter how big you give to VGS, like 5 volts, you don't give a pressure to the 2 channels, it's not going to move the electrons. Okay, so like a pipe, you have to, put a pump on one side to give a pressure, the water can flow. Same concept. You need to turn it on and to give a pressure. So that's for NMOS. For PMOS. Just delete it. Press F2 and find PMOS transistor. There's a hidden rule here, which is you can see the gate is not in the middle, and it's always closer to the source. So, for example, if you grab NMOS here, and you want to tell like which one's source, which one's drain, it actually doesn't matter because the C5 is symmetric. But it's better to have a good practice over here. So the gate is closer to the source. So this gate is the source. This is drain, right? If you rotate it and you put a high voltage here, use it as a drain, it's still gonna work the same way. But it's just not a good practice. Same as the PMOS. PMOS is also have a gate on the top. Instead of have N plus here, you have a P plus. P plus as a source and drain. And you're wondering like this is a P type. Is that shorting to the ground, shorting the source and drain to ground? Yeah. So you have to put the P plus in the N well. That's a process, right? To isolate it. It's not shorting to the ground because the P type substrate is always shorted to the ground, right?
So always at least one class have P-type substrate?
Yes, yeah, yeah. So the P plus, the PMOS, the P plus has to be in the N well because the substrate is the P type. So if you put a voltage here, for example, this is source, this is drain, this is gate. And for this case, we are not looking at VGS. Instead, we look at VSG. Keep in mind. VSG. VSG means S has a higher potential and G has a lower potential. All right. Okay, so for NMOS, we have VGS, G has a higher potential, S has a lower potential to turn it on. And now we have to do VSG. So it's a lower potential here and higher potential here. So the lower potential, the negative charge at the gate is going to attract holes from the N well to form a channel with holes. If you ground the drain, and the hose is here, and the drain is grounded, what's going to happen? You got a high potential here, right? And ground is relatively lower potential. So the hose is going to move in that direction to form a current. So the PMOS symbol looks like this, has a little bubble in front of it. So you usually put a source on the top because source need to be high voltage. You're saying, hey, it's not forming a current, that's not forming a circuit. You're right. I didn't put a VSD here, so it's not going to work. That's all the things you need to run currents through the PMOS. First, you need to turn it on. How to turn it on? Apply a VSG. Is G, do you need to ground G or not? Keep in mind, I didn't say VG or VS. I'm saying VSG. Keep in mind, VSG. Okay, so VSG has to be larger than the threshold voltage of the PMOS, which is 0.9 volts in this case. And positive 0.9 volts from S to G. Okay? Do I need to ground G? You don't have to for this case, okay? So I just said we need a VSG. I'm not saying it has to be an absolute VS or VG. It's a relative voltage or potential difference between S and G. It's gonna work. So you just need a certain voltage between the S and G, the difference between two terminals, which is larger than 0.9 volts to turn it on, to turn on the channel. However, there won't be any current flow in the channel because you don't have the pressure. Okay, so you need to apply pressure to S. Now you form a current. These are both grounded. These are shorted together physically. Okay? So the current is going to flow that way to ground and back to the source. All right. So that's the symbol in the schematic, and this is the drain. And you need to turn it on here, apply a potential, and you need a VSG. So what are the typical voltages for this guy? I mean, using 5 volts, just to put a 5 volts as a voltage difference of the channel. It's going to push the hose to the drain. Okay? And What about this one? It just needs to be larger than 0.9 volts. And the connections can be different, but you are only looking at if all the voltages between the terminals are meeting the requirement. Okay. Sometimes it looks really weird. For example, let me see what they did in the past. I have to look at the schematic again, but so this is a PMOS schematic, and if we put it in LT-Spice, remember the gate is closer to the source. So this is basically, this is the source. If I'm gonna put the source on the top, I have to rotate it. So the way to rotate it is drag it and wait, I believe it's Control R. Control R. And I don't like the gate on the right hand side, so I can measure it. So just put it here. You have to do it fast. You know, if you don't do it fast, it's going to keep moving your screen. Right? Do it fast. And put your cursor towards the mouse on the top and measure it. Okay. And put it here. Okay. On top is source. Okay. So now we need to connect. We need to give a voltage difference between the source and gate. So I'll just use this one. Put on the top. Okay, I have to call it the SG. F3 is VS. This is G. It's 3 volts, larger than 0.9, right? I'll give this one 5 volts. And keep in mind, for the PMOS, you have to short the body to the highest potential in the circuit, keep in mind. And we'll explain why later, okay? But let's just do it. You're wondering, how do we do that? What is the highest potential in the circuit? Where is it? So we said for the NMOS, the middle pin here is the body. So the body of the NMOS is a P-type substrate, right? The wafer. So what is the body of the PMOS? What is the body of the PMOS? Where is the PMOS being fabricated in? The N-well. So the N-well is the body of the PMOS. And the P-type is the body of the NMOS. So what's happening for the whole wafer is, because there are billions of transistors, but I'm just showing 2 of them over here. So for example, this is a piece of the wafer, cross-sectional view. You got a 1 transistor here, which is NMOS, right? NMOS. You don't need to do anything. You don't have to put in the N-well because it's already N+. It doesn't make sense to put it in the N-well. So the N+ is in the P type substrate. So the P-type, the wafer itself, is the body of it. And then you got a PMOS just next to it, like the inverter, right? You have a PMOS on the top, NMOS at the bottom. I actually have a lot of PMOSes very close to NMOSes. So you got a PMOS over here, also has a gate. And that's P+. However, this guy has to be in the N-well, right? Just put N-well here. You know how to draw N-well. We have done that with a resistor, right? And this is a P substrate. Sometimes I put a P stub. Sometimes I put a P dash type, P type or P sub. All right. If you want to short the body or the P type substrate to ground, what you are going to do is you put a P plus here, right? And you ground it. Then your whole body is grounded. Do I need to put this P plus in the N-well? This P plus? Do I need to put it in the N-well? Why? Why not? Yeah, I need to short it to the ground. I don't want to isolate it. That's why I put a P plus over there, because P plus is the same material as the P type substrate. So they are considered as shorted to each other. So if I short this little node to ground, I'm shorting this entire P sub to the ground. What about this guy? How do I short the body of the PMOS to the highest potential of the circuit, like VDD? How do I do that? I want this N well to be connected to VDD. Similar to that, the way I did for the P sub, what can I do for this guy to short the body of the PMOS to VDD or to the highest potential of the circuit? No. The other N plus is a terminal of the transistor. You don't want to interfere with that one. That's an individual PMOS, right? It should do all the business within that PMOS instead of messing up other transistors on the circuit, in the circuit. You just fabricate a little N plus over here, right? Implant N plus here and connect it to VDD. Make sense? The N plus is shorted to the N well because they are same material. So if you short this one to VDD, you short the entire body or N well, which is the body of the PMOS, to VDD. Okay. If you look at the lab, no, not that one. Okay, so here. Let me find a better picture. So this one, okay? So this is a NMOS, okay? That's an NMOS. That's an NMOS transistor. And don't worry about the slashes. These are just different layers in the fabrication, okay? And you can see that the pink one in the middle is a gate, okay? This is the top view. You are looking from the top. And these black nodes are vias. So they connect the terminals here to a top layer, and then you have another layer on the top, runs metal traces. It's called metal 1. That's the first layer of metal. So what's happening is so all the transistors are built or fabricated for follow the bottom up process. So you have a wafer here, and then dope well, then dope the P plus, okay, and then have another layer here, and leave a via. So the via is a metal, the hole that can put a metal. Like PCBs have different layers. You can run metal traces like these metal traces to the top, and then on the top layer you can have the metal traces running, so you can make the connection, right, to the metal 1, and you have another silicon oxide layer to insulate the different layers. So they're not getting shorted. And then drill a hole to the top. We use the vias, right, the via, and then have another layer of metal, and then drill holes on the top, another layer of metal. Just keep going to the top, and then you can eventually, you got a chip. You can look from the top to look at the chip. The hole, you can leave holes at the edges of the chip, so you can make the connections to the metals. And eventually, these top layer of metals will have connections to the bottom and to the very bottom transistors. So this is the very bottom layer of the chip. So for this one, this is the channel. The green color here is the channel. only the width of the gate defines the length of the channel. I don't know if that makes sense. If you look at the drawing here, see the width of the gate. Okay, if you look from the top, the width of the gate is the length of the channel. So that's the length of the channel. Why? Because all the holes or electrons will move along that channel, so that's the length. And that's the width of the gate. Okay, if I look from the top, look at it from the top, it looks like this. I got one question for you guys. Where did I cut it to make that cross-sectional view I just showed you in the drawing in the paint window? How do I cut it in order to, and then look from the side to show the same view as what I just drew here? Where should I cut it? Do you agree with that? So cut here, right? And look from the side. Cut it here and look from the side. You got two terminals, right? Two terminals, and the gate on the top and channel. Can you imagine that picture? Okay. So keep in mind, only the distance underneath the gate is a channel. All these are something else. So only this is the length of the channel. And this is the width of the channel. Okay? And these are the terminals. You got two vias because this is probably too wide for just one via to be here. So I got two vias. It doesn't matter. They're just two metal, same piece of metal piece. Okay? Two vias. And that's the terminal of the N plus, the Nmost is going to be N plus over here, N plus. Okay, and it connects to the top metal layer. So the via will drill a hole up, and then you can run metal one. Okay, so this is a gate material. It's called polysilicon. And the same thing. So if you look at the gate, it's just above the transistor. So you also need a via here, right? You need a via connect to the layer just on the top of it, right? And then run metal one on it. It's the same thing. So that's how you connect the gate to metal one. You're not directly put a metal one or via on the top of here, right? So what you do is extend it and then put a via here. So this via will connect it to the upper layer, which is metal one, and make a connection to the metal traces. Okay. So Nmost is fabricated in the P style. Okay. I might be wrong, but I think if you look at the different colors of dashes, I think the black dashes here represents the P style. Okay. And this is a P plus node. If you look at the drawing here for Nmost, so this is the Nmost transistor, right? So this is Nmost. Every time I have an Nmost here, I need a P plus to be next to it. So I'm showing the Nmost transistor spotting to ground. The reason is I want to keep it close to the Nmost transistor. So that's why every time I just put a little P plus next to the Nmost. P and NMOS transistor, they share the same substrate. The way to do that is you grab a P, I think this one probably is P act, okay? You grab a P act, P well maybe, not P act, I'm sorry. It's a P well. So keep in mind, you don't have P wells, it's a P sub. So it's a P plus, okay? And you grab this guy, and you put it here, you can see they have the same dash. See, this guy has the same dash, the black dash at the background. So that's the same substrate. And you don't have to make any connections. You just move them close enough that they have an overlap of their substrate. And whenever they're being fabricated, they'll be put in the same well. So the P well here stands for P sub because we don't have a P well. The P sub is a P well. Or the body is a P well. The entire wafer is a P well. Makes sense? So you see the dashes? And this material is a P plus. So the P plus is being put in the P substrate. The dashes are P substrate or P well. Okay, that's a P well. N plus in the P well and P plus in the P well. And you want to make, so after grab this one, you move them close enough so we can see the dashes are overlapping with each other. So in that case, it's not going to report any errors. If you don't overlap them, it's going to report errors. Keep in mind, you don't need to electrically, physically shorten anything together. You just grab one of these and resize it, and then move it close enough so they overlap, the dashes overlap. Done. So you are not going to get any errors to be reported. Okay, so that's the entire version, a complete version of NMOS. You got N plus, you got a P contact. So P contact or P plus in the P well is called a P contact. It's just the name of it. It's being connected to the P well probably, that's why it's the P contact. Right. So let's look at the picture and see if I was wrong or not. So for the P well or P act, which one we are supposed to use? I believe it's a P well. See, when you at the very beginning, okay, for NMOS, so grab NMOS first, put NMOS, but it doesn't have an N plus, okay, and then grab N plus. So N plus is N act. So the name of the N plus is N act. So put an N act here, another N act here. All right, and then you have to make the connection to it. So connect them. So before do that, you grab a polysilicon to metal one via, and eventually, so it's a P well. So I was right. So put a P well here as a P contact, which is the P plus in the P substrate. So this guy, the P well. And keep in mind, we don't have P well again. It's a P substrate. So it's a P plus in the P substrate. P plus in the P substrate, which is here, right? I'm just placing it over there. I'm going to readjust it and resize it and move it around and make the connections later. Okay, see, this is P well, but all the other two nodes are P act. These are P act, which is P plus. What's the difference? What's the difference in electric VLSI? You can tell it looks different, right? They have different colors. So what's the difference? Keep in mind, you are physically laying out a chip right now.
whatever being laid out here will be reimaged. They have a very sophisticated machine to do that for lithography, right? $1 billion piece. Another one, the name of it, ASML, a company. It's the only company making 5 nanometer EUV lithography machines in the world. Their stock prices over $700 for one stock right now. ASML combined with TSMC is probably taking like 90% of the share of the market.
Are they both in Taiwan?
No, Netherlands.
Oh,
ASML.
there's another big foundry in Taiwan, right?
UMC, not that big. $7.9 per share for UMC. It was 10 and dropped to 8. Now it's 7.9. But TSMC is 88 now. It was 150 and now dropped. Still, the Federal Reserve, the interest rate is too high. Anyways, the demand is low. These people are struggling right now. What's the difference? They are both P plots, right? P plots, but in a different place. Why they have to put a different layer here? Why they have to specify that this P plus is in that shadow or in that slash, different slash represents a different layer? Why they have to specify that? Because I'm just telling you, these are the real physical view for fabrications. Right? If you put this layer there, if you send it to TSMC or send it to GlobalFoundries, they are going to make the exact layer for you. It's going to be a certain chemical being deposited on the silicon wafer. So you are telling them what you want to fabricate in the chip. It's not a schematic anymore. It's a physical view of the chip. Right? So this is the NMOS, I guess. NMOS or PMOS? NMOS. Or NMOS, right? So this is NMOS. NMOS, NAT, okay? NAT is N plus. N plus in the black dashed line, which is a P sub. So directly put N plus, you deposit N plus into the P substrate. And P well is a P plus in the P substrate. Why? Because we need that guy in the P substrate. You see, you don't have a well here, right? Directly in the P sub. N plus in the P sub. N plus in the P sub. So they are in both P sub. So if you look at the dash, they have the same dash, the black dash. So they are in the same P sub. For PMOS, see, there are dots. The P plus, the P act, which is a P plus here, the P plus here, is being fabricated in the dots. The P act or the P plus is being fabricated in the dots. See the little background, the dots. And the PMOS must be fabricated in N well, because N well is the body of the PMOS. So the N well is N plus material being fabricated in the No, it's just N plus material. You don't see the dots. They are N plus material. So one quick question: why it didn't specify the background? Because everything here has to be on wafer, right? Which is the P-type substrate, but didn't show that, right? You know what I mean? You know what I'm saying? If you look at PMOS, the P plus are in the dots, right? The N plus in the dots. Okay? But behind the dots, it didn't show anything like the sub or something, right? It didn't show the dash. What's really happening here? See dots, but I'm not seeing the slashes. This should be fabricated slashes in the P substrate. And just by default, these are all in the P sub. So it didn't show that. Okay. But for the NMOS, they have to specify that. You know, that's just the rules in this software. You don't have to worry about all the slashes. I'm just showing you, like, when we'll see the different colors, different dots or slashes, you know what's going on, right? And sometimes it makes sense because, or you have to know it because you have to move it close enough to overlap them in order to get error-free the report. Okay. And there will be a few simulations, I believe, but you run it from here, and it's going to bring up the window in LT-SPICE and do the simulation. If you see something like that, don't worry about that. It's just the orientation of the currents. You can replot it. Remember how you can do that? For example, I run this guy. If I'm giving VSG, if for example, I'm sweeping VSG, do a DC sweep for VSG, and I'm commenting out this guy and run it. So if I probe current here, so this is very different. You can only show this current probe at the drain, not the source. Okay, so for example, in this case, it plots the current in the opposite way, and you want to present it in a different way, like going up instead of going down. How to do that? It's right click, right? Right click, and addresses. You put a minus sign in the front of it. ID, right? You delete the blank one. Okay, that's for the presentation purposes. If you want to show it the other way, because the reason for that is the current probe here, you cannot change the direction of it. If you plot it, it always shows that direction. Okay, if you don't like it, just add a minus sign in the front of it. Okay. Any questions by far? So I think the examples over here show a 4-terminal device, and I think it shows you how to change it. Just make it a default connection, so you don't have to use 4 terminals. But I believe at the very beginning, I didn't use the 4-terminal device, I think. Let me see. See, at the very beginning, I didn't use that 4-terminal device. By default, in electric VLSI, they short the body of the animals to ground and short the
body of the PMOS to the highest potential in the circuit. But I think just follow this tutorial, it should work out fine. Okay. You have options here. You can see you can choose 3-terminal or 4-terminal device. This one doesn't have the body contact or the body terminal, but by default it's connect to ground for the NMOS and VDD for the PMOS. Okay. All right, just follow the tutorial and let me know the challenges you may have. All right.